This is part 5 of the series Relationships Within Triangles, and we're going to start this part by looking at the triangle inequality theorem. The triangle inequality theorem says the sum of the lengths of any two sides of a triangle is greater than the length of the third side. Now, I like to get a visualization of this because it might be kind of cryptic when you look at it at first. So let's take a look at a graph. So here we see in triangle ABC, AC is 7, AB is a little bit more than 4, and BC is a little bit more than 3. So clearly AB plus BC is greater than 7. So what happens if it isn't? Notice how when I pull these down, these numbers are getting closer and closer to 4 and 3. And when I get really, really close, you can see that these numbers are almost exactly 4 and 3. And so when B is on AC, AB is 4, BC is 3, and AC is 7. Clearly, there has to be enough extra material in either AB or BC so that we've got just enough to pop up that vertex. If this is exactly 4 and this is exactly 3, then we wouldn't have enough to make AB plus BC longer than AC, and so it can't bow up like it does here. So that's the nature of this theorem. And the farther we get away from AC, you can see that the larger the difference is. Now this works no matter where we put it. If we make one side 12.4, 6 plus 7 is greater than 12.4. It's actually 13.248. And so you can see that no matter what we do to form a valid triangle, the two segments in the middle have to be greater than the longest. So you can see that 7 plus 5 is 12, and this whole long side is 12, so this does not make a triangle. When we move it just a little bit higher, now this value plus this value is just a little greater than that value, so it works. It's actually a triangle. It's a very obtuse triangle, but it works nonetheless. So I hope you have the idea behind the triangle inequality theorem. And now what we're going to do is we're going to try and figure out, given two lengths of a triangle, what must the third length have to be? Or in what range does that third length have to be? That's what we're going to work on with these next examples. So in our first example, we have a triangle with one side length 14 and another side length 9. We need to describe the possible side lengths of the third side. Now, the way to take care of these is, the way I would take care of these is to organize them. So I'm going to organize them from smallest to largest sides. So we have 9, and then we have 14. We know that the sum of any two must be greater than the third. So what we have to ask ourselves is there any value smaller than 9 that when added to 9 will give us a number greater than 14? Well, the answer to that question, of course, is yes, because 8 plus 9 is going to be greater than 14. So there is going to be a number to the left of 9. And there will be a number greater than 9 because 9 plus 10 is greater than 14. And then we have to ask ourselves, what number would 9 and 14 be? Because is there a number to this side which would be greater than 14, but 9 plus 14 is less than that number? And the answer is yes. So our possible range is some number less than 9 and some number greater than 14. Now the easiest way to take care of this is to say, well, what is 14 minus 9? That would be 5. And what's 14 plus 9? That would be 23. Now, since we know that one side has to be 9 and the other side has to be 14, we know that the smallest side has to be greater than 5 because 9 plus 5 is equal to 14. So whatever value we pick for our side length, it's going to have to be greater than 5 for that reason. Also, we know that 9 plus 14 equals 23, so our third side can't be 23. It has to be a little less than 23 because 9 plus 14 has to be greater than that third side. So whatever value we pick has to be less than 23. So we can say that the possible side lengths for the third side is greater than 5 and less than 23. Anything greater than 5 and less than 23 would work in a triangle that has one side of 9 and one side of 14. All right, well, let's try that one more time in the next example. Here we have a triangle of side length 12 and 20. So again, I'm going to organize these by smallest to largest, and we do the same idea. Is there a value to the left of 12, smaller than 12, that will add up to give us a number greater than 20? Yes, there is. There is a number between 12 and 20. And what about greater than 20? Yes, there is. So we do the same basic process. We're going to take the biggest number and subtract the smallest number from it. So 20 minus 12 gives us 8. And 20 plus 12 gives us 32. So we know that whatever value we pick for x, it's going to have to be greater than 8 because 12 plus 8 is equal to 20. So this number has to be greater than 8. And 12 plus 20 is 32. So the number is going to have to be less than 32. So in this case, our possible side lengths for the third side are between 8 and 32, non-inclusive. That is a number greater than 8 and less than 32. So let's go look at another example. Here we have a triangle with a side length of 4 and a side length of 9. So just like we did before, we're going to put our smallest side and our biggest side down. Then we ask, is there a number to the left of 4, less than 4, that added together gives us a number greater than 9? Well, the answer to that one is no. But then we ask, is there a number between 4 and 9? And the answer is yes, because 6 is between 4 and 9, and 4 plus 6 would be greater than 9. And so, is there a number to the right of 9 that when we add 4 and 9 to? Well, yes, there would be one there. So in this case, what we're looking at is a number between 4 and 9. So we're going to want to do the exact same thing we did up here. We subtract the smaller from the bigger. Subtract the smaller from the bigger. 9 minus 4 gives us 5. And 4 plus 9 gives us 13. So we know that our value, whatever we pick for the value of our third side, it's going to have to be greater than 5 because 4 plus 5 equals 9. And so this x value is going to have to be greater than 5. And it's going to have to be less than 13 because 4 plus 9 equals 13. So the range of possible values is between 5 and 13, non-inclusive. All right, well, let's look at a different type of problem that we might encounter. Here we're to decide whether it's possible to construct a triangle with side lengths 4, 9, and 10. Using the theorem, the triangle inequality theorem, we know that the sum of any two sides has to be greater than the third. So the easiest way to do this is to just add up the two smallest sides. If the two smallest sides come out to be bigger than the largest, then the answer is yes, they can construct a triangle. 4 plus 9 is 13, so it's greater than 10, so yes. we can construct a triangle. Do the same thing for the next one. Decide whether it's possible to construct a triangle. 8 plus 9 is 17. That is less than 18, so no, it is not possible to construct a triangle with side lengths 8, 9, and 18. And then the last one, 5 plus 7 is equal to 12. So again, we have a no. We cannot construct a triangle because it would have to be a little bit bigger than 5, because 5 plus 7 equals 12. All right, well, I hope that cleared things up, and let's move on to the last section. In this section, we have two related theorems, the hinge theorem and the converse of the hinge theorem. Now, these may seem very similar to the triangle longer side theorem and the triangle larger angle theorem, but the triangle longer side and larger angle theorems dealt with one triangle only. The hinge theorem and converse of the hinge theorem deal with two separate triangles. The hinge theorem says, if two sides of a triangle are congruent to two sides of another triangle, and the included angle of the first is larger than the included angle of the second, then the third side of the first is longer than the third side of the second. So here we have AC congruent to DF, CB congruent to FE. So two sides of one triangle congruent to two sides of another. The included angle here is 124. The included angle here is 97. Therefore, the side opposite the larger angle is longer than the side opposite the smaller angle. That's all there is to the hinge theorem. And the reverse also applies. If two sides of one triangle are congruent to two sides of a second, and the third side of the first is greater than the third side of the second, then the angle opposite the third side of the first is greater than the angle opposite the third side of the second. So again, two sides congruent to two sides, larger side, larger angle, smaller side, smaller angle, and vice versa, larger angle, larger side, smaller angle, smaller side. So let's see how this works in examples. So in this example, we're given that ST is congruent to PR, and we're asked, how does angle PST, this angle right here, compare to SPR, this angle here? So since PS is congruent to itself, we have two sides of one triangle congruent to two sides of a second. The third side of one is bigger than the third side of the second, so we can say that angle S is bigger than, angle PST is bigger than angle SPR. So bigger, smaller, because bigger side means bigger angle, smaller side, smaller angle. So let's take a look at another example. Here we have JK is congruent to LK. How does JM compare to LM? Well, again, we have KM congruent to itself by the reflexive property. So two sides of one triangle congruent to two sides of a second. Bigger angle translates to bigger side. Smaller angle, smaller side. So we can say that JM is bigger or longer than ML, smaller or shorter. So the hinge theorem and converse of the hinge theorem are pretty straightforward theorems, and it just requires making sure that you have two sides of one triangle congruent to two sides of another. Well, I hope this helped, and I'll talk to you in the next session.